This is chapter 6, part 2, moving on from slide 16. So now we're modeling trend with ARMA noise, and we're going to start with a general signal plus noise model. Yn is mu n plus eta n. Eta n is going to be stationary. We're going to suppose eta n is mean zero, which is basically the definition of trend, right? So the trend is all in mu n, which is the mean function. This is a generalization of a model we saw before. If eta n is uncorrelated, we have signal plus white noise. Now, that's what we used for, that's the usual least squares regression model that we saw in chapter 2. When you just say signal plus noise, people might accidentally think you are talking about white noise. So you can say signal plus colored noise to be explicit that you're not assuming white noise. Signal and trend are used interchangeably, and so that basically means when you call the trend the signal, that means you're assuming a deterministic signal, essentially, because the trend is the expected value, which is deterministic. Now, given where we're at with developing ARMA theory, it's natural to consider an ARMA PQ model for this stationary noise process eta n, and in particular, we'll suppose that it's a stationary causal invertible ARMA model with mean zero. Okay, and one of the reasons this is so useful for data analysis is that there'll often be unknown parameters in the mean function, and in particular, we can use explanatory variables in the mean function that we're interested in. Does some other variable help to explain our time series? That leads us to really the very useful technique of linear regression with ARMA errors. So suppose we can make a reasonable linear specification of the trend where mu n is the sum of the znk beta k's, where beta k is some collection of coefficients and the znks are the covariates. In this case, when the eta is ARMA, we have a linear regression with ARMA errors. And let's just put this into the kind of notation of linear models. If we write y for a column vector of the data, mu for a column vector of the means, eta for a column vector of the noise process, and we'll often use z for the design matrix of the regression. We shouldn't use x because we normally use x for a time-dependent process, and so we have the general linear regression model with correlated ARMA errors now is written y equals z beta plus eta. Now, when in, I think, chapter 1 or 2, we were looking at the regression with white noise, and we said, well, if you don't do least squares, you need to make some sort of assumption on the covariance matrix of the errors, and then you could do generalized least squares. And now we're really in a situation to talk about good covariance structures for time series data, because we have the class of ARMA models which specifies a covariance structures, depending on which ARMA model you pick. So likelihood evaluation, numerical maximization of model 4 can be built on ARMA methods. In particular, y minus z beta is ARMA in this model. Okay, so we have the ARMA function in R that knows how to calculate and numerically maximize the ARMA likelihood. And we just saw that regression with ARMA errors we can rewrite as an ARMA model, so we can do maximum likelihood estimation using the same numerical methods for this parameter vector theta, which has the unknown ARMA parameters and the unknown vector beta parameters for the regression model. And as usual, we should look out for signs of numerical problems. We can look for likelihoods that don't satisfy nesting conditions, for example. But basically, data analysis for linear regression with ARMA errors follows the same path as fitting an ARMA model if you use this likelihood-based framework. And we can put any covariates of interest in Z, and potentially we can draw inferences about mechanistic relationship between dynamic processes that are represented in the beta. We have to be very careful of doing this because most time series are they're not experimentally randomly perturbed data, so it's observational data, and so we have to be very careful of not jumping to an assumption of causation when we've demonstrated an association. Well, so let's do this in the context of Lake Huron depth. A very simple type of trend is a linear trend. And so let's start by looking for a linear trend using a regression model with Gaussian AR1 errors. So we already found that AR1 was a reasonable model for the error process in this case. First of all, we'll fit a null model with no trend just as a benchmark. Here we go. This is just the AR1 model fitted to this Huron depth data. There's one little detail I wanted to point out for you here. When you see the log likelihood of 22, you might think, why don't we get any significant figures here? Does it only think it's accurate to zero significant figures, for example? Well, what's really going on here is that R drops trailing zeros. And that's kind of a problem because as a good applied statistician, the trailing zeros are a statement of numerical accuracy. And so you don't want to remove them. And what I do for that is I load this R library Broman and use my round, which knows which in fact dropped to 0 here. So, well, I was about to say it knows how to, I see. By default, my round rounds to 1 decimal place. So, but it does keep the trailing 0, which otherwise R tends to drop. Well, now for comparison, let's compute as fit1 a linear trend model. The new thing here in the coding is how you tell R what is the covariate, and turns out that there's an xreg argument to ARMA. And so if I want a linear trend on year, then I put xreg is year when year is the variable I constructed. And so here you go, we have a fitted model which we can compare to the fit 0. I guess fit 0 is our null hypothesis that there's no trend. Fit 1 is an alternative hypothesis that has a linear trend. And so we're maybe interested in testing how strong the evidence is that there is a trend, or are we just maybe imagining that we see a trend in chance variation of a dependent process? We can set this up as a formal hypothesis test. And so for that, you have to write down the model, the hypotheses. And we've done this enough times now, so it's not very novel, but we write down our model as something like in equation 5. The form of the mean is mu plus beta Tn, and so this is the general form of the regression with AR1 errors, and epsilon is going to be Gaussian white noise with variance sigma squared, because we might want to do likelihood-based inference, so we do need to make a parametric assumption about the white noise. And then our null hypothesis beta is 0, and our alternative hypothesis is beta is not equal to 0. And now we've set up our hypothesis, we're in the business of doing a test. So there's a couple of different ways you can do the test. And perhaps the most obvious thing that might come to mind for you is to make a z-test on the slope parameter, which here is beta, and our test statistic is going to be our estimate of beta divided by its standard error, which I think is minus 0.0. These are just from the previous slides. 0.0049 was the estimated slope, and 0.0019 is its standard error. And so we see that this difference is well over 2 if I the absolute value of beta hat over SE beta hat is greater than 1.96. So this lets us reject H0 at the 5% level. That's just a standard normal approximation hypothesis test. And the other thing we can do is we can do a likelihood ratio test. Often just abbreviated to LRT. Let's see how we're going to do that. Let's call delta the difference in the likelihood. Well, difference in the log likelihood, so it's corresponds to a ratio. And the well, let's just check what these things are. So this likelihood here is 24.62. And the other one, right, was 22.00, which is 2.62, and it's 1 degree of freedom. We know what the likelihood ratio cutoff for 1 degree of freedom is here, which is bigger than 1.92. That's from Wilkes's theorem. Again, we reject H0 at the 5% level. Maybe I could have calculated those p-values, but I can't do it so easily right while I'm talking. Okay, so which test do we think is more accurate and why? Well, we saw in the previous chapter that the Fisher test can be unreliable. Actually, very much for these data. From chapter 5, we may trust the likelihood ratio test more than the Fisher standard error. And you might even have to think, why is this a Fisher standard error? Well, it's a Fisher standard error because R is doing exactly what it does with ARMA models. It's calculating beta hat by numerically estimating the second derivative of the log likelihood it's at its maximum, which is the Fisher information. Okay, how would we check whether our preferred test is indeed better, and what supplementary analysis could we do to strengthen the conclusions? This again is just what we did in chapter 5 to investigate methods for standard errors of ARMA models really extends to regression with ARMA errors. So what should we say? What we did last time, we did a simulation study which is essentially another name for a bootstrap. What these do, if either or both approximate tests, right? And this is the two tests here are a Fisher normal approximation and a Wilks likelihood ratio test. Are accurate for this sample size. These simulation studies of bootstraps won't find problems with the model, they'll find problems with these approximations. If you want to check the model, residual analysis and trying alternative models can reveal if there is room for improvement in the model itself.